Today, I'm happy to introduce Professor Keith Christian. Keith is a physiological ecologist. He got his PhD at Colorado State University, and after a postdoc in Wisconsin and a professorship in Puerto Rico, he came to Australia to work at Flinders and has been now at CDU since it started, for over 35 years. So Keith's work focuses on physiology of reptiles and amphibians, and his PhD was on Galapagos land iguanas, and since then he's worked with a variety of other herps. And today he'll be presenting some synthesis work on generalizations in comparing tropical and temperate herps.
Okay. Thanks, Hava. Okay, so in general, when organisms are faced with a changing environment like climate change, if they're going to survive that change, they have a couple of different options. One is to change over generations, that is, change by way of evolution if they have the genetic material to do that. Or the other possibility is that individuals can change physiologically, and that's the topic of today's talk. That I'm referring to is physiological plasticity, or it can also be referred to as acclimatization, so within an individual's lifetime. So a few things that is this one on? Yeah.
Good times. The click doesn't work either.
Not looking. This is working.
I think it just worked. Yeah, try the left click will work.
Left click.
Yeah. The left click is working.
Yeah, the light came on and it came off again. Anyway, sorry about that. Technical. I'm glad I'm not going for a job interview. So a few things this talk is not about. As I've mentioned, it's not about genetic change. And it's not about, I'm not going to really talk about other consequences of climate change, such as incubation temperatures might change and might cause problems for animals. Trophic collapse might cause big changes in food availability, loss of habitat, and so forth. So the point is that there are a lot of potential problems with climate change. I'm not going to address all of those. I'm talking about the possibility for an individual to adapt to climate change within its own lifetime. So I've been working on animal physiology for more than 45 years, and my ideas about it have changed over time. And those changes have reflect a lot about where I have lived and worked and had the opportunity, animals I've had the opportunity to work with. And so I'll start the story with, this is a Galapagos land iguana. This is a male. This is a female. But the important part about this slide is that these shrubs aren't dead. This is just what the dry season looks like in Galapagos. And then the rains come and these shrubs look like that. And so the iguanas eat the leaves of these shrubs. They eat the flowers of these shrubs. They eat the fruit of these shrubs. They also eat the apucha cactus, but they can't reach that until something falls to the ground. So there's a much greater food availability in this after the wet season starts. Yeah, that's up. Let me see. There we go. All right, now the keyboard's working. All right, so one of the things I found in this study was that I wasn't looking for it, but I found that this is body temperature of the iguanas. These are grand mean temperatures of quite a few animals in different days. Across the day, you can see that in the warm, wet season, this is the plot of body temperatures, and this is in the cool, dry season. So this wet season value is very typical of an iguanid lizard. So they cool down overnight passively. Early in the morning, they come out and bask. Their body temperature comes up to their preferred temperature, and then they start shuttling between the sun and the shade and keep a very constant body temperature until the late afternoon, starts cooling down again, and the whole thing starts. Well, this is very typical for an iguanid or an agamid lizard of body temperature around 35, 37 degrees during the midday body temperature. This is very atypical, and this was a big surprise to me. And so, as you can see, they're doing the same thing. Early in the morning, they're basking, warming up very quickly, but then it levels off, and their body temperature is about 5 degrees cooler in the middle of the day compared to the wet season. So the question then is that because it's cool and they can't get any warmer than that? Or is it because they're preferring to be cooler in this season? And the way we answered that question was using biophysical models, which are what we call a mechanistic model. It's sort of like if you had modeling or calculating, if you had a glass of water that was at 10 degrees and a glass of water that was at 40 degrees, if you added a certain known amount of these two amounts, you could predict using a mechanistic model very precisely what the temperature would be of this combination. And in this case, we measured air temperature, wind speed, solar radiation, direct solar radiation, indirect solar radiation, reflected solar radiation, so on and so forth, and put those into a model that also had characteristics of the animal, its size, its reflectivity, and so forth. And we can say, okay, and given this set of environmental conditions, what would the animal's body temperature come to? And because it's that sort of a mechanistic model, if you have good input data, you can predict very precisely what the body temperature of an animal would be under those conditions. So if you had it out here if the animal's out here in the open, it would be one thing. If it moved under this sort of semi-shade, it would be another body temperature. And if it was under deep shade, a different body temperature. And the answer is that, if I can go back, yep, the answer is that, in fact, these animals in the cool, dry season could be much warmer, which really makes sense. You wouldn't expect this temperature to rise that quickly if this was the limit. In fact, they could come up much higher. They could get up above the temperature they want to be. They could be up close to a lethal temperature. But of course, for a shorter period of time, because the morning is so much cooler, but they could get as warm as they want, much warmer than they would ever want. So this represents a behavioral shift. And I explained this in my PhD thesis. I didn't know the answer for sure, but I came up with a couple of different possibilities, a couple of different hypotheses, put those in the thesis. And it turns out one of those was right, but it was only some years later that I came to Darwin that I was able to answer the question really definitively, and I'll come back to that point later. So after spending time in Galapagos, my next tropical experience was in Puerto Rico, and where I was a lecturer for a few years. And as you can see, Puerto Rico is a very different kind of tropical environment. And that's because on any given day, it's like there's a pretty high probability of it raining. So these are the rainfall, monthly mean rainfalls in San Juan, Puerto Rico. And as you can see, it could rain any time. Now that doesn't stop the people in Puerto Rico and Costa Rica and Panama from talking about a wet season and dry season. But when they're in Puerto Rico, when they're talking about the dry season, they're talking about this. And as Darwinians, we can say, you call that a dry season? This is a dry season. So this is what our dry season looks like. And interestingly, the rainfall of San Juan and Darwin, the average annual rainfall is almost exactly the same. But this is spread evenly throughout the year. And we have our seasonal patterns of rainfall. And that has profound effects on the vegetation, as you saw in the previous picture, but also on the way the animals live in those environments. So I'm using this relationship to talk about two main parts of the tropics. We can call this the wet tropics or aseasonal tropics, and I will be referring to places like Darwin and Galapagos as the seasonal tropics or the wet dry tropics. So when I moved to Darwin, one of the first animals I wanted to work with was the most, spectacular animal to work with, and so we studied frillneck lizards for several years, and as it turns out, frillneck lizards do exactly the same thing as land iguanas, even though they're insectivores, not herbivores. So in the wet season, they have a mean midday body temperature of 37 degrees, 36, 37, and that is about 5 degrees cooler in the dry season. And again, like in Galapagos, we use biophysical models to show that it's not that they can't get that warm, it's because they don't want to get that warm. They go up. So at this time of year, in the dry season, they're up in the same trees they're in the wet season, but usually a little bit higher. And in the morning, they turn to the sun, warm up really quickly. But then when they get around 30, they move around to the shady side of the tree and spend the rest of the day sort of shuttling like this, literally moving a few centimeters, regulating their body temperature around in the low 30 degrees. Again, I found that interesting, but it didn't really answer the question of why. Next species that we worked on was this animal. Every time I publish a paper on it, they change the name. And we've got some data now, hoping to get that published before we miss out on Tropica gamma before they change it again. But for the purposes of this talk, I'll refer to them as Tata lizards. Tata lizards do the same thing. They regulate in the high 30s in the wet season, in the low 30s during the dry season. And as it turns out, all of these animals do the same sort of thing. Quite a range of different species have seasonal shifts in their preferred or their midday body temperature in the field. These are animals, body temperatures measured by radiotelemetry of active animals in the field. So this took up a lot of the 1990s, but not every species that we measured has that same pattern. This is Merton's water monitor. They have about the same midday body temperature throughout the year, as does the mangrove monitor. And this is the Varanus panoptes, or the so-called floodplain monitor. And the floodplain monitors were really the key to my understanding this in a much more complete fashion. And that is, even though they're called the the floodplain monitor, they're often found around billabongs or floodplains or streams, but they can also be found right out in the middle of the savanna. And we were able to measure animals in both of those two different kinds of habitats Those that live close to water act like water monitors, and they maintain constant midday body temperatures throughout the years. Those in the middle of the savanna act like frill-neck lizards or land iguanas. They seasonally change their midday body temperature. So that was a big clue that it has something to do, wherever you find water, you find goanna food. And that suggested to me that what's really driving this is the availability of resources, food and water. Now, based in Darwin, as opposed to in Galapagos, we were able to measure a lot of other things in addition to just measuring field body temperature. At the same time, we were bringing animals into the lab, measuring metabolic rate and some other things that I'll mention in a minute. But so this is the Tata lizard again. I could show you a very similar graph for frill-neck lizards and Varanus scalaris and all of those species that were in a slide a few minutes ago, where we have, as a function of body temperature, again in the laboratory experiments, this increasing body temperature, we have log metabolic rate. I'll talk about log metabolic rate and unlogged metabolic rate in a few minutes, but the purpose of logging it is that you get these nice straight lines that are easy to do statistics with and so forth. So as you can see, the metabolic rate at any given body temperature is higher in the wet season than in the dry season for Tata lizards and frill-neck lizards and so forth. I suspect the land iguanas, but I was never able to measure that. So what that means, or what this is referred to as metabolic depression. So relative to the wet season values, in the dry season, they have a depressed metabolic rate, lower metabolic rate. And in the case of the Tata lizard, that's a very profound drop. It's about 65% depression. And so it's less than half of their metabolic rate at a given body temperature. And I'll talk about some of the mechanisms, a little bit about the mechanisms of this a bit later. And it turns out Tata lizards are not alone. Also frill-neck lizards, Varanus scalaris, and some of these frogs and turtles all show a similar pattern of metabolic depression in the dry season relative to the wet season. Now, for the Tata lizard, this is Tata lizard again, but also we did the same thing for frill-neck lizards and a couple of the other species. We were able to measure additional things. A big one being activity, and that we did this again by radiotelemetry, and this was back in the 90s. Now you can do this sort of in an automated fashion. We did it all manually. It was very time consuming, and you had to follow animals or had to have big antennas and keep the animals in range and so forth. So it was very work intensive, but it was very rewarding to get the results. And what this graph shows is the energy saved. This whole pie here represents the energy saved by Tata lizards in the dry season relative to the wet season. So in other words, if you had a kilogram of Tata lizards in the dry season, they're using 147 kilojoules less energy than they are in the wet season. And that's represented by this whole graph. And we were able to subdivide that, figure out, well, what are they doing to save this energy? Start here with this green piece of pie. This is nighttime body temperature. So this is a pretty passive. They can select where they sleep, and that has a bit of effect of how quickly they cool down, but really they're always going to come to something close to air temperature. So this is pretty passive. But all the rest of this pie, the animals have something to say about it. They can do something either behaviorally or physiologically to achieve this reduction. So I've already talked about daytime body temperatures being lower. about 5 degrees in the dry season. That accounts 14% of this total energy savings. Talked about metabolic depression. That accounts for about a quarter of it. And about 35% of it is because they're less active in the dry season than they are in the wet season. So as you notice, you don't see field-neck lizards very often. You don't see tartar lizards as often in the dry as in the wet. They're still around, but they're much less active, and so they're less conspicuous. One other thing that's not shown in this graph is that we were able to measure is we were able to measure food consumption by a technique, fairly invasive technique called stomach flushing, where you take an animal and you flush the food out of its stomach and you can figure out how much it's eaten. And based on that, we show that they're not eating much in the dry season. And that's just a reflection of there aren't nearly as many insects in the dry season as there are in the wet season. So the food availability is much lower. So based on that, the food that they're taking in, we were able to calculate sort of the energy budgets of an animal in the wet season and in the dry season. And we came to the conclusion that this metabolic depression and these changes in activity and so forth are not just sort of party tricks that these lizards can do to impress their friends or anything. They're really fundamentally important for their survival. There's not enough food around for the animals to maintain a high metabolic rate, high levels of activity, high body temperatures in the dry season. They have to do these things to survive. So I said I'd talk a bit more about this metabolic energy. The previous graph showed the log of this value, which gave you a straight line. But the logarithmic form, just a straight, if you measure metabolic rate and plot it on a straight linear axis, you'll get a graph like this. And the reason I want to show you this is to illustrate the importance up here at the high body temperatures. A little change in temperature makes a big change in energy, both in energy expended, but energy expended means energy that they have to acquire by food. Whereas down here at the low end, it can kind of slop around and change body temperature and has very little metabolic, very little energetic consequences. But up here at the high end, it really matters. And so in the tropics, you know, we kind of, everybody's all bundled up and thinks 18 or 20 degrees is in Darwin is cool, and it is, but compared to in the temperate zone of 5 to 10 degrees, it makes a big difference because the difference between 20 and 25 or 30 and 35 makes a big difference in energy, whereas the 5-degree difference down here is not much difference in energetic consequences. So the next step is to show the consequences of that previous graph in two different animals. These are two animals in the same genus, two different goannas. Varanus rosenbergi from Kangaroo Island, so a temperate zone species. Varanus scalaris from locally. And again, these bars represent energy saved in their off season, so to speak. This is energy saved, again, units of energy per kilogram per day. So this bar represents the energy that a Kangaroo Island iguana, a goanna, saves relative to a summer Kangaroo Island goanna, and this represents the energy saved in the dry season for Varanus scalaris relative to the wet season. So obviously they're both less active in their off seasons and save huge amounts of energy by being less active. They're both cooler, and particularly in on Kangaroo Island, where cool means 5 degrees, that has a big energetic change consequence, but also to a lesser extent in the local species. But look at metabolic depression. Interestingly enough, these two species both have, just by chance, exactly the same degree of metabolic depression. It's 50%. So in the metabolic rate at a given body temperature in the dry season is half of that of what it is in the wet season. But half of of an animal at 5 degrees is half of a very small number. So it represents very small energy savings. Half of an animal, of the metabolic cost of an animal at 25 degrees is quite a big energy savings. So for the Stellaris, it represents a really big part of this energy conservation during a period of low resource availability. So armed with this information, back in 1999, two postgraduate students of mine at the time, Gavin Bedford and Tim Schultz, and I wrote a paper entitled Energetic Consequences of Metabolic Depression in Tropical and Temperate Lizards, where we argued that if temperatures are high during periods of inactivity, or relatively high, so in the tropics versus the temperate zones, metabolic depression will result in big energy savings, which I showed you in the blue part of that previous graph. We also concluded that therefore we would expect metabolic depression, that is physiological plasticity, to be very well developed in reptiles from the seasonal tropics. That was 1999. We kind of sort of said, okay, I've got a pretty good idea. I know why Galapagos iguanas now are regulating their body temperature at lower body temperatures. I bet they have metabolic depression, but I haven't measured it. The other animals I've measured. So I have metabolic depression. Those that live near water and high resource availability don't show the pattern. So I really thought I sort of understood what was going on in this system, and I moved on to different things and started doing different kind of work from the 1990s. So it was much to my surprise that last year, in 2022, I saw a paper in Ecological Monographs entitled Higher Metabolic Plasticity in Temperate compared to Tropical Lizards Suggests Increased Resilience to Climate Change. In other words, the exact opposite of what we said in 1999. And so I said, wait a minute, that doesn't sound right to me. And I started looking into it a bit more. So before I get stuck into this paper, I'll just say that there's quite a bit to like about it, despite the fact they didn't cite any of the 25 papers or so that we published in the 1990s. But what I like about it is that they did burrow down into the physiology and the biochemistry of what's going on with respect to metabolic depression. And so that's a good thing. But there were problems with it. First of all, they studied 3 species, one of which was a tropical species, sort of. It was barely on the edge of the tropics. It was really a subtropical species. And they came up with 3 physiological patterns. By that, I mean 3 different physiological biochemical mechanisms of plasticity. One of them one species decreased the size of the liver. Another species changed the biochemistry in the liver. Another species changed the sodium pump or something like that. So 3 different mechanisms to achieve the same goal. So if I had done that work, I would have, instead of this title, I would have said something, named the paper something like, lizards find 3 different ways to skin a cat, or something like that, because that's what's really important to me about that. But instead, they chose a title that makes this big generalization about tropical animals, which is contrary to what I thought I knew about tropical animals. So they had to support that. They only had 3 species, one of which tropical. So they had to pad out, this is a monograph. This is not just a little paper. This is an ecological monograph. They had to support this generalization with a lot of literature, and there were two main ways they did that. First, they used literature about thermal tolerances of tropical lizards to say that a lot of tropical lizards that have been studied have very little tolerance to adjust their body temperature. If it gets too hot, they suffer from that. And the second line of evidence, or second theoretical context that they used to make their argument, was they used the climate variability hypothesis, which is sometimes called the Jansen hypothesis, named after the guy Dan Jansen, who came up with it in 1967, which posits that tropical organisms should possess lower physiological plasticity due to the reduced thermal variability under which they have evolved. But I have problems with both of these lines of support. First of all, the evidence for the thermal intolerance of lizards, tropical lizards, is almost is exclusively from the wet tropics. Puerto Rico, Costa Rica, Panama, and tropical Brazil, or wet tropical Brazil. There's been lots of studies on lots of different species of lizards in those areas, and they are thermal intolerant, but that's the wet tropics. Another problem is that as we all know, anybody who's lived in Darwin for the last 4 months know that the thermal environment in the tropics can be pretty variable compared to Puerto Rico, because most lowland Costa Rica, and so on and so forth. So I could have put up a plot there of the San Juan temperatures, which would be very stable compared to the Darwin temperatures. So the wet tropics tend not only to be constantly wet, they tend to be very much more constant in their temperature than the seasonal tropics that we're more familiar with. But most importantly, in the first part of the talk, I talked about the fact that physiological plasticity is driven by resource availability and variability. Resource availability and variability. And by the resources that I'm talking about are food and energy, water, and these two often go together. And I actually include thermal resources, the thermal environment as a resource, the way I've approached it using those biophysical models and so forth. So I'm not excluding temperature. I'm just saying temperature is part of the story. Both food and water are also very important components, resources that can sometimes be limiting. So what do we know about these two different sort of tropical environments? In the wet tropics, thermal resources, food and water, are less variable and probably not limiting. In the seasonal tropics, all three of these are more variable, and food and water can be limiting, as I talked about earlier with some of the local animals. And that results in physiological plasticity. So the climate variability hypothesis could much be better if it's restated. To say organisms that have evolved under conditions of stable resource availability, low thermal variability, constant food and water, tend to possess lower physiological plasticity. But that's regardless of latitude. That has nothing to do with the tropics. It just has to do with their resource availability. Or you could look at this from the other way around. Organisms like our local organisms that have evolved under conditions of resource variability, thermal variability, food and water, will exhibit physiological plasticity with respect to limiting resource, to those resources that are limiting, regardless of latitude. So it's not a tropical temperate thing. It's not a, it's a resource availability phenomenon. Now, Hava, there was some help from Clem, I think, put together these numbers and to show the reason that you can't really gloss over the wet dry tropics, because the wet dry tropics consists or comprises about a third of the tropical landmass, whereas only about a quarter of the tropical landmass is what we call the wet tropics. And so there's been, at least in the reptile, or at least in the lizard physiology literature, there's been a very disproportionate bias towards the wet tropics compared to the wet dry tropics. But you can't ignore the animals in the wet dry tropics. So there are still a lot of things that we need to know about this topic. As I said, most of the literature they cited about thermal tolerance was from the wet tropics. What about thermal tolerance in the seasonal tropics? That's not something that we studied in the 1990s. So I can't show you any data. I can't even show you any references. I suspect, or I would hypothesize, that it's much more plastic than the wet tropics because our temperatures are much more plastic than the wet tropics, but it's still an unknown, really. The relationship between different plasticities, different physiological factors. So I've talked about thermal preference, so the body temperatures that the animals choose in the real world. There's thermal tolerance, there's metabolic plasticity that I've been talking about. There's also evaporative water loss, which we've been studying. Cade and other postgraduate students have been studying much more recently. The question here is, what is the relationship? If one changes, do they all change? You could hypothesize that all of these would be co-adapted, and that if one changed, they would all change. There's very few studies that have measured more than one of these at a time. And so it's really something we need to know, but I can just say, without giving away Cade's seminar, hopefully in a couple of months, that the evidence that we do have shows that they don't necessarily change in tandem, that some of these things tend to change, as far as we can tell, independently of one another. And that's just a big unknown. I could say more about that, but I won't. The limits of plasticity. In other words, we know that a lot of animals that have thermal plasticity can change, can adapt to higher temperatures, and animals that have metabolic plasticity can adapt to periods of lower food availability and so forth. But what are the limits of that? Is it going to be enough for animals when the temperature rises or the food availability changes? And then there's also heritability plasticity. So plasticity itself can evolve. So at the beginning of the talk, I sort of separated evolutionary change from physiological plasticity, but of course they're linked, because heritability or plasticity can evolve and does evolve. And so then the question is, well, what are the limits of the genetic potential for changes in plasticity as climate changes? And so there is the potential there for another way of animals adapting their changes changing their response to the environments by the plasticity changing. But of course, this is something that we really know pretty much nothing about at this stage. So in summary, the Jansen hypothesis has been around since 1967. It's been a very valuable heuristic tool. That is, it's inspired a lot of different work, a lot of different studies. But really, as it's stated originally, it's time to give it up as a broad generalization. It's not a broad generalization. The broad generalization that we should be making is in terms of resource availability and variability. Those are the factors that determine physiological plasticity and the ability to respond to environmental change. Another generalization that I think we can probably safely make is that because of what we know about the resource availability in the wet tropics, that ectothermic animals like these lizards I've been talking about probably are more vulnerable to climate change than animals in both the temperate zone and in the seasonal tropics or the wet dry tropics. And to be fair to some of the people who've made this assertion, Huey and Mike Kearney and others, they tend to limit that assertion to the wet tropics. And whereas the paper that I'm talking about that came out last year generalized about the tropics and didn't separate the wet tropics from the dry tropics, which brings me to my last generalization, which is you probably should avoid sentences starting with organisms in the tropics, because the tropics are quite variable, and there's no reason to think that animals living in the tropics wouldn't also have variability, variable responses to those variable environments. So thanks for your attention. Question?
Thanks, Keith. I really enjoyed it, and sorry for coming in late. I was just wondering, have you done any of this metabolic rate work or activity movement work in species like tautau lizards in urban environments? I'm just thinking to my own backyard and watching tautau lizards around our compost bin, and that year round they are just going to town on the insects and the maggots and all sorts of things that are crawling out of there. And I'm just wondering if it's, urban environments are less resource limited, and if you might expect changes in urban environments.
Yeah, that's an interesting question. I guess I would say that there's variability in urban environments, so that the scenario you described, where there's a big source of food and animals are coming to it, might be really different. But from the urban environment, we did sample the tautau lizards. This is back when we were at Miley Point, and we caught them at the Fanny Bay jail. And so that's an urban environment, but there really wasn't much irrigation going on. And so, I think they were responding pretty much as the ones out in the savannah would do. With some of the other more recent work, we've been catching geckos, and some of the species of geckos, a couple of species, are easier to catch on buildings than they are to find them in the bushland. But interestingly enough, we found seasonal differences even on buildings or where they've got lights and insects coming to the lights. And so, yeah, I think it just depends on the severity, or I think if you really watered an area and really had food and the insects came, then you could probably recreate the wet season. But most urban environments aren't that extreme.
Yeah, fair enough. Thanks.
So Keith, with those authors, are you just festering in discontent, or are you bringing them to account?
No, we've Hubba's helped me, and Gavin, who helped back in the 90s with some of the field work. The three of us have written a comment to ecological monographs, and that's still in review, but I think it'll be published. Unfortunately, the way ecological monographs publish their comments is that the title of the comment has to be the title of the original paper with the word comment behind it. So we can't come up with a title saying, no, you're wrong, you know. But anyway, if somebody goes to the next step and reads the paper, they'll see the.
Well, the authors will.
Yeah. Yeah.
Do you think that, where do you think the dry tropics stands in all of this? That other third of the tropics and lizards there, do you think they're similarly vulnerable as those in the wet, or do we just really not know enough about them?
Well, we know very little about them physiologically, and there's a lot of survey work done. So again, this would really be sort of from tropical Capricorn, which is just locally is just north of Alice Springs. From there to say Tennant Creek, that's a big area, or even a bit further north. It's a big area. There's a lot of animals there, but there's very little physiological work done on those species. My best guess would be, I don't know. I think it's very variable. It's very variable. But there's the potential that it could be so extreme. So particularly with respect to a really arid environment, the aridity may be so extreme that they're sort of fixed. They have evolved to that environment to such a point that they're fixed on that really low, on that mechanism of survival, whatever that might be, low rates of water loss, or whatever, or seasonality. Yeah, I think that's a really interesting question. I don't know. Every time I think about it, I come up with a different answer. It's variable, which would suggest that it might be like the wet dry tropics, but it might be too extreme for them to really to exercise that full variability. Because when you think about it, the environment we're in is like a boom and bust, you know, and sure, it's in the desert, it's boom and bust too, but it's much less predictable. You'll get rain, but it's often not nearly as predictable. And so it's a different kind of boom bust environment. Yeah, no.
Surely, last week, I think it was impressed upon us that the future is variable rather than that it's warming. We can take it as certain that it's warming, but it's warming at such a slow rate that the ectotherms would not be affected in their choice of full sun radiation and warm rocks and whatnot, but they would certainly be affected by the variability of their rain and therefore their tucker.
Yeah. I would agree with that. And so these people who are arguing, when this idea about the wet tropics came out, it didn't sit with me, you know, I hadn't done that much physiology in the wet tropics, so I didn't really have the data to address it, but it didn't sound right to me because of, as you mentioned, the animals can move between sun and shade and regulate their body temperatures. But these particularly Huey has demonstrated that even in the shade, because these animals are so intolerant of an increasing body temperature, even in the shade, it might be getting too hot. And so I think there is some danger for some really specialized forest animals in that regard. Those that are living in, in the clearings of the forest probably have much more flexibility, but those really rainforest species that have evolved there may be trapped and may have a ceiling. There's just not the genetic, there may not be the genetic variability for them to increase their tolerance.
There's a chat.
Okay. Chant.
And it is not a question, so.
Okay, thank you.
Do you have any other questions? Thanks, Keith.
Okay, welcome.